everyone, my name is Ataberk Akgül and this is my EE474 magnetic resonance imaging project presentation. For my project, I simulated the Bloch equation and altered certain parameters of it in order to check out how they affected the magnetization in the X, Y, Z directions. So you can see here the Bloch equation. The one on the bottom is the solution in matrix form. So basically I simulated this equation in MATLAB and found out how parameters such as T1 time, T2 time, phase angle, the system being off frequency, the excitation numbers and parameters like this, how they affected the overall magnetization. So let's get back into our code. The code is pretty straightforward. Initially I declared these variables, T1 time, T2 time, repeat time is 1 second. As for T1 and T2 times, I took the values for gray matter. The M0 value is 1 and the number of excitations is 5. The flip angle is initially 90, which is what is mostly used. And the code basically also as the axis of rotation, I selected the y-axis. This is the rotation matrix for the y-axis, and after the magnetization, the decay and recovery times are found like this. These formulas are pretty straightforward and can be found in the book. So also, of course, the initial rotation is towards the z-axis. So this is the rotation matrix for the z-axis. So this for loop stores the magnetization in terms of x, y, and z in a matrix called M. And the rest is the plot sequence. So let's run this. This is the magnetization for gray matter. As you can see, after the 5 excitations, the overall plot, initially the MZ value is equal to M0, which is 1, and when it is excited it jumps to 0, and the MX value jumps to 1, then it decays and the MZ value recovers while the MX value drops down as time passes until the next excitation occurs. And the same process is repeated, but this time from a lower part, because the repeat time was lower than the time required for it to resume its initial state. The magnetization in y-axis is always 0 because it is flipped in that direction. So that was my base of operation as a form to compare with other values. So in this part I increased the T1 value, which is the time required for the X and Y Z direction to recover, and when it is increased, this value increases to this peak point because the T1 recovers faster. When T1 is decreased, the MZ recovers faster, thus increasing much more. And if T1 is increased, the opposite occurs. The peak of T1 comes lower, and the codes are pretty much the same thing with the parameter changed. So in this part I decreased it to T2 time, and this affects this MX value dropping. It becomes steeper because the drop time decreased, and it becomes steeper, and if T2 is increased, the opposite thing occurs. For the third part, I applied a 60-degree flip angle instead of 90 degrees. As you can see, the MZ axis is not fully excited, and it drops like down to 0.5 from 1, because sin 60 is 1/2, so this is logical. The other values are pretty much the same, but the flip angle changes this value. And in this part, I lowered the TR time and the excitation number. The excitation number pretty much determines the total duration of the simulation and has no other effect on the data points in terms of magnetization. And also I decreased the TR time to 500 from 1000. My initial simulation was 1000. Since it is lower, the MZ value doesn't get up as much as the previous step, and it is excited again as it is increasing, so the value is about 0.4 compared to the 0.7 that we saw prior. And also in my previous simulations, the off resonance frequency was 0, so let's see what happens when this is 10. As you can see, if the frequency is off resonance, this equation, this part changes, so the angle of rotation in terms of RZ changes, and this adds a sort of ripple in the MY and MX directions. As the resonance increases, this ripple increases to a point that you can distinguish each fluctuation. And in this, the MY value is not constantly 0. It has some values. So this could alter the resonance imaging. And so that was my project. Thank you for listening.